So today I'm going to find the second largest element in a binary search tree, and I have on a whiteboard next to me two trees drawn out, and yeah, they have the numbers 27 as the root, and then left child would be 14, right child would be, well, I'll just list all the numbers that are in my tree. We have 14, 33, 31, and 35, with 27 as our root. And I have them drawn out in two different ways. One of them has 14 as the left child and 35 as the right child of the root 27. And then, according to the rules of binary search trees, the left child of 35 is 31 and the right child of 31 is 33. That way the left subtree is always smaller than the parent, and the right subtree is always larger than the parent node. And on my other tree, it's a little bit more balanced, but not completely. We have 27 as the root again, and 14 is still on the left, but instead of 35 as the right child for 27, we have 33, and then 33 has two children, 31 and 35. And by drawing the trees out in this way, I've come to the conclusion that we always know that the largest is going to be the rightmost child, starting from the root. And now what we want to find though is the second. So the largest is the rightmost, and the second largest will be either two options. We have, it could be the parent of the largest, or that would be the case unless the right node, largest node, has a left child. In this case, it would be the largest of the left subtree. And given that information, we can now find out the second largest. So I'm going to start by creating my function. It's going to be called second largest, and it's going to take a binary search tree, and this will, let's see, how do I write functions? Okay, so now what we need to do is we're given this binary search tree, and the first step is right here. We need to find the largest. So I think I'm gonna, pull that out into a second function because I'm gonna need to use it again. So this will find the largest. And now what we need to do is first we'll check if it's a valid binary search tree. And we'll check if it is. If it's not, we're gonna just return null. Otherwise, we want while. We're gonna keep moving right until we reach that point where right is null. So while binary search tree is a value, we're going to set binary search tree equal to binary search tree dot right. And I believe after the while loop finishes, we will end up with our binary search tree. the largest. So this will be the largest. So now what we can do is I've copied over a dummy somewhere to fill in my tests. So now I kind of want to create a binary search tree so that I can do my tests. So I'm going to create that here. I'll call it binary search tree, and it's going to take in a value and a parent. That way we can easily find our parent because we will need it in this problem. So we're going to set our constructor function. We have the binary search tree needs the value, which is given, and it'll have a left and a right defaulted at null, and a parent that will either be parent if it's given or null. Next, we need to write an insert method so that we can add children to our tree. So we'll do binary search tree dot prototype dot insert and set this equal to a function, and that function is going to take a value. And now what we're going to do is we are going to, so we know that the current node that we're inserting is going to be this, so I'm just going to call it current node, set it equal to this for easy reference. And what we want to do is we want to check if current node dot value is greater than value. We're going to want to insert it to the left of the current node. So next we gotta check if the left child is null. If that's the case, so if current node dot left equals null, then we're gonna want to insert a new binary tree. So we'll do current node dot left equals a new instance of the binary tree. We'll pass in the value and the parent, which is current node. So we're going to want to do the same thing on the right. So that can just be an else case. We'll have an extra case just to make sure that if current node dot value equals value, then we're going to want to return kind of like an error. So I'm just going to put false. And then, just to make this look better, I'll make this an else if. So now our last case is that current node dot value is less than value, and we know we want to insert on the right. So we'll go if current node dot right equals null. Then we want to do the opposite. So I'll just place this over here. Current node dot right, and we need to handle our else case in both of these situations. Otherwise, we're going to want to let's see. We're going to want to invoke insert. This is using recursion. So we'll want to do current node dot left dot insert value. And here we're going to want to do current node dot right dot insert value. So I wrote this function and now I want to check to see if it works. So I'm going to create a new binary tree. I'm going to call it test, I guess. And we're going to set it equal to binary search tree, new binary search tree. And we're going to pass in the example I was talking about earlier. 27 will be our root, and parent will be null. And then we want to insert, so we'll go test.insert. I'm going to insert all of mine that I talked about earlier. So 14, 33. Let's see. We know we want 35, 31, and I think that's it. So now I'm going to just console log test to make sure I didn't make any mistakes so far. Okay, so it looks like I have my root of 27, left of 14, and it looks like I made a mistake somewhere. I forgot about, let's see. So parent is circular, that's okay. Let's see, so root is 27, left is 14, and 14 actually looks right. 14 has a left of null and a right of null. Right is of 33, and then left is 31 and right is 35. Okay, never mind, I think it looks good. So now let's go back to writing our second largest and our largest function. Okay, so now I want to test out largest. So I am going to, let's see, I am going to need to, let's see, do I export these? Yes. So I'm going to want to export my functions so I can test them. So I might do that as an object, and we'll do largest, will be largest, and second largest will be second largest. You know what, I'm going to change this. I'm just going to need second largest because that's what the problem's asking for. And to make sure that my largest function is going good, inside second largest, I'm just going to console.log largest of the binary search tree. And what I'm expecting is, in my test case, to insert this tree, and I'm expecting a result of 35. So here I'm going to console.log largest, the second largest, and I'm going to pass in test. And what I'm expecting is 35. So second largest is not defined. Oh, let me try it again. Okay, so it looks like, I think it said it's null. So instead of console logging, I'm gonna return. That way it'll hopefully show up on the test. Second largest is null. Why is that? So let's see. So for for some reason it returned null, and we're gonna set, let's just console.log binary search tree to see what's going on. It's null. Now let's do it above the while loop. Okay, it's not null above the while loop, so that's good. So now what we want to do is figure out what's wrong with my while loop. So I think I know. So we want to check while it has a value. Well, first we know, according to this if statement, that we will have a binary search tree. So we're going to set our current node equal to binary search tree dot right. And then while this is not null, we're going to want to set it equal to right. And then we're going to want to return it. So let's see if this works. No. So let's see. Binary search tree dot right is another binary search tree. And eventually it's gonna be null. So let's see. Current node equals current node dot right. It's because we're setting current equal to current node dot right, which we know is going to be null once we exit the while loop. So there's our problem. So to fix that, I'm going to set a temporary variable equal to current node, and then set current node equal to current node dot right, and what we're going to return is the temporary node. There we go, that looks better. So we got our, it's saying second largest, but it's our largest, and that's what we want. So now that we know that our largest function works, we want to find our second largest. So to do that, we are going to want to given our binary search tree, we want to first find our largest. So I'm going to set it found large, set that equal to the largest, which in our case will be 35. And then what we want to do is check if found large has a left child. Then we know that then we need to return the largest of this subtree. Otherwise, we want to return the parent of the largest. So this is pretty easy. We just return found large dot parent. And then here what we're going to need to do is we're going to need to return the largest of found large dot left. And I think that's actually all we have to do. So let's test it out. We have our second largest console log here. which we're expecting 33. And let's look at another test case. And we want to assert that 33 equals second largest test. And something that I just thought of is we probably are going to want to return the value. So here it would just be .parent.value, and here it would be temp.value. Whoops, I got a semicolon in there. Okay, so let's see if this works. Cannot read property value of undefined. So let's see. Let's get rid of our values and see what happens. Expected 33 to deeply equal object. Okay, before this test case, I'm just going to console log second largest. Make sure that it's working. Cool, we got 33. So I want my second largest to return a dot value. So dot value, this will be a node and it'll have a value. And then largest, we want to return temp.value. Why wouldn't this work? Cannot read property value of undefined. I'm just going to take away this one. Okay, second largest is undefined. So okay, we found the whole node. Maybe we can return the whole node. So what I'm going to do is I'm going to set a variable called second, and I'm going to assert that second dot value is equal to 33. And it seems that that passed. So thank you.